Okay, so let's start. Any questions last time? Correct. So right now, what are we doing? We're essentially picking a graph, a bipartite graph at random. Or in other words, we're picking a parity check matrix at random. Now, what can happen is, since you're picking it at random, there is no guarantee that all the rows are going to be linearly independent. Correct? So since some of the rows could be dependent, it means that the actual dimension of the code is different from k. So if it's it's different from n minus m. So in particular, since the rate is since the rank could be less than or equal to n minus m, could be even strictly less than n minus m, the rate, which is actually n minus m by n, the rank could be strictly less than m. So the rate is n minus m by n, so it's going to be greater than or equal to n minus m, the actual rate of the code. Right? So that's all that this is saying. So the question is, how much larger can the actual rate be greater than the design rate? And this statement is basically saying that the probability that the actual rate is greater than the design rate. By design rate, I mean n minus m by n. Exactly. So this is what we have in control. But then because of the randomness, the actual rate could be larger. Question is, how much larger can it be? Now it turns out that under some conditions, as long as you can have a very small gamma such that the actual rate is not too much larger than the design rate. In fact, for irregular LDPC codes, you can show that the probability that it is greater than 1 plus some epsilon, or maybe let me call this 1 plus delta, is vanishingly small. In fact, this probability decays exponentially with n. For the case where it's a regular LDPC code, in fact, you can make a much stronger statement. So in this case, the design rate, let's say that I choose the design rate to be, let's say 0.3. So what this is saying is that probability that the actual rate is greater than 0.301 or something like that is vanishingly small. For regular LDPC codes, in fact, it turns out you can make an even stronger statement. And that statement is the following: the probability that not the actual rate itself, but so for codes, that show that the probability that n times the actual rate. Right? So this is the actual dimension of the code. Right? Probability that this is greater than n times the rate for which you designed plus some constant nu. I'll just explain what the nu is in a moment. This is vanishingly small. This little of 1. Okay. What is nu? So in the previous case, the extra factor that we added, was 1 plus delta, right? So in particular, if you look at n times r of g greater than n times r of say lambda rho plus n times delta. So you could design for a dimension which is, let's say, 10,000, but the actual rate could be 10,100. And the probability that it's greater than, let's say, 10,100 is something very, very small. But in this case, you can make a tighter statement. So in fact, this is nu is equal to 0 if DVDC, because since we are dealing with regular LDPC codes. Okay. Even. So this particular probabilistic statement that I'm making depends on whether dv is odd or dv is even. So if dv is odd, then the probability that the actual dimension is even one more than the designed dimension decays with n. The probability is maybe, let's say, 1 over n. But if dv is even, then the actual dimension of the code will never be equal to the design dimension. Okay? But the probability that it is greater than 1 plus the design dimension decays with n. So why is there a difference between the case when dv is odd and dv is even? The difference is because if dv is even, what does it mean? If you look at the parity check matrix, right, what is dv? dv is basically the number of ones in each column, correct? And we're trying to find out basically what is the rank of this parity check matrix going to be equal to, right? Now if dv is even, you've designed for this, what happens if you sum up all the columns, sorry, all the rows? What would you get? It would be even parity, correct? Which means that the rows are all linearly dependent. They're not, all the rows cannot be linearly independent if you choose dv to be even. So the actual dimension is either one more than the design dimension. So if this is an m by n matrix, then the actual dimension is never n minus m, but it could be n minus m plus 1. Right? And the probability that it is greater than n minus m plus 1 is vanishingly small. That's the only statement that we make here. Right? So let's do a quick recap of what we've seen so far. So originally, what did we start out with? We wanted to design codes which were kind of capacity achieving for a given channel. And right now our focus is the binary erasure channel because it's the simplest channel to deal with. So we started off by constructing this class of codes called LDPC codes. Encoding is anyway simple because all you have to do is matrix multiply. So that's why we stuck to linear codes. And now decoding for LDPC codes is similar because we drew ideas from the generalized distributive law. Okay? And for LDPC codes, we have a very efficient algorithm. Unfortunately, we don't know how well this would work. So at least if we try to do simulations, it seems to work out well. But then we don't know how to design good LDPC codes or so, not yet. So the first sort of assumption that we made was that even though the graph or the factor graph is not exactly a tree, we'll still run something similar to the generalized distribution. That gave us the message passing or the belief propagation. And then we even further simplified that for binary input channel. You want to design binary LDPC codes, then decoding is as simple as just passing real numbers across all the edges. It's an iterative algorithm. Now again, the question was, how do we design a good LDPC code? When we did some simulations and we saw how things performed for regular LDPC codes, we started with 3-6 regular LDPC codes. The capacity should have, at least we should be able to get a small error probability for any p less than 0.5. and above 0.5 anyway, you're above capacity, so there's nothing you can do. But then we saw that the probability of error was small up to around 0.4, but beyond that it was shooting up. So it means that there's something wrong. We don't know whether LDPC codes themselves cannot achieve capacity, whether it's a fundamental limitation of the code itself, or it's a fundamental limitation of the algorithm itself. And is it possible to somehow jointly optimize it? So now we have an algorithm. Now the goal is to design a code which works well with this particular algorithm. And to do that, we first need to understand why it didn't work well. So why is it that the threshold is at 0.4 and not higher than that, right? And to do that, we're trying to sort of develop the theory in a slightly more general fashion. So instead of just sticking to regular LDPC codes, we're now considering irregular LDPC. So now instead of saying that every row and every column has exactly DV1s or DC1s, we're now saying that a proportion of the rows can have say D1 ones, another proportion can have D2 ones, and so on. So that is formalized by this idea of the degree distribution. So, and we saw 3 different ways of specifying the degree distribution. One was this lambda of x, which is the degree distribution from what I call the node perspective or the vertex perspective, which is basically this polynomial where the coefficient of x power I is the number of variable nodes having degree I. And similarly in P of x, the coefficient of x power I is the number of check nodes which have exactly degree I. And then we saw this from the normalized, we also saw the normalized degree distribution, which is L of x is equal to lambda of 1, P of x R of x equal to P of x divided by P of 1. So in actually going from lambda of x to L of x, we're actually removing some information. In this case, you're only looking at the fraction of variable nodes. So it doesn't really depend on what n is. So this is a quantity which is independent of n. And we'll see that our goal will be sort of to analyze LDPC codes in the asymptotic limit. So instead of characterizing specific LDPC codes, we are going to characterize classes of LDPC codes, all of which have the same degree distribution or normalized degree distribution. Now, at least for analysis, we'll see that it is helpful to look at this from a different view. So instead of looking these 2 polynomials, we'll instead look at the following polynomials: lambda of x, which is lambda prime of x divided by lambda prime 1, and rho of x is p prime of x divided by p prime of 1. So this is the coefficient of x power I minus 1 is basically the fraction of edges which are incident on a node having degree I. So again, this is another way of looking at this particular quantity. They give the same amount of information, so both R of x and rho of x give the same amount of information. The only difference is that when we'll try to analyze the belief propagation algorithm, these 2 things sort of naturally arise. Okay. So of course, you also need a way to go back from the lambda to the small lambda to the capital lambda, or the small lambda to L of x, and it's very easy to verify that the following holds. So L of x is, again, since this is obtained by differentiating things, this is simply equal to integral 0 to x of z dz, but this has to be normalized. So this is divided by integral 0 to 1 easy. And similarly, r of x integral z divided by 0 to. So given the whatever the class of LDPC codes, either in terms of L and R or lambda and rho, you can always go back and forth between. And in henceforth, we'll mostly use lambda and rho to specify a particular family of LDPC. So okay, so now we know how to sort of characterize LDPC codes, or we split these into families. But now we need to actually analyze LDPC. How do we know which LDPC codes are good? How do you design good LDPC? And for this, to analyze things, we'll make the following two assumptions. The first one is not so much of an assumption, but in fact a sort of a fact, but that will greatly simplify things. So the first one is actually a simplification more than an assumption, although historically it's been called an assumption, so we'll use the same term. So the first assumption or simplification is basically the restriction to the all zeros code word. So by this I mean that we will always assume during analysis, people always assume that the all zeros code word is transmitted. And the reason why this assumption can be made, or why the simplification can be made, is because the BP algorithm, or the probability of error, for BP algorithm is the same irrespective of which code word is transmitted. The probability that, let's say, the all zeros, the probability of error given that the all zeros code word was sent, is the same as the probability of error given that some other code word, non-zero code word was sent. And since we're picking a code at random, we're choosing, what we're going to do is we'll fix a degree distribution. We look at the class of all LDPC codes which have this particular distribution and pick one random code from it. And for this, we're going to use the configuration ensemble. So therefore, assuming that you're drawing it from this, the actual code is actually random, but all code words have, all codes have the same degree distribution. And it turns out that since we're using this belief propagation algorithm, it doesn't matter which code word you're setting. And therefore, it's good enough to assume that the all zeros code word was set. And that's a big simplification, because no matter which code you pick, the all zero sequence is always a valid code word, because it's a linear code. So that's why we'll make this one big assumption, or one big simplification. And the second sort of assumption or simplification that we will do is the following. Second is, we basically study the performance. By performance, I mean the code word fit error probability. for random codes. Basically, what do we do? Let's assume that we fix a particular degree distribution, lambda and rho, and using the configuration method, we pick one code uniformly at random. We pick one graph that completely specifies the code. And then we study, okay, for this random code, what is the probability of error? And in order to analyze that, we'll make again a series of assumptions. And that is because of properties of sort of most codes in this particular ensemble. So again, so in many of these, I will not prove all the statements because that will take a very, very long time, and there's a lot of other techniques that one will need to that will need to be introduced. But I'll still give you an idea of how some things like this can be proved. So first, the question is, okay, now you're picking a random code, and why is it good enough to choose a random code? So no matter how I pick the code from this class of codes, the overall decoding complexity is still going to remain the same, because the complexity is governed by the degree distribution, and every code that you pick from this ensemble has the same degree distribution. So complexity wise, we are fine, both encoding and decoding. The only problem is that some codes could achieve a smaller bit error probability, some codes could give a higher average bit error probability. And since it's a huge class of codes, right, a huge number of codes in this particular class, it's possible that some will perform very badly and some codes will perform very well. Right? So just looking at the average is not enough. But then what one can show is that if you pick a graph G, a random graph from the configuration model, right, then the probability of error under belief propagation decoding for a random graph drawn according to the distribution lambda and rho, the probability that this is too different from the average error probability of belief propagation decoding for the random graph drawn from this greater than any delta is less than or equal to e to the minus r. So as n tends to infinity, if you're interested in very large block length codes, then if you pick any random graph with very, very high probability, this will achieve the same as the average error probability for a random code drawn from this. So what this essentially says is that if we can prove that this average error probability is small, then if I draw a random code, then this code is also going to be good. It is going to achieve roughly the same probability. It is not the case that many codes are very good and or some codes are extremely good and there are many codes which are bad. That is not the case. If you pick a particular degree distribution and it turns out that on average the class of codes performs well, then if you pick a random code, then most codes are going to perform well. So what this implies as a designer is that now instead of sort of carefully choosing a particular code, all I have to do is carefully choose a degree distribution. So if it turns out that that degree distribution is good in whatever sense, then I don't have to worry any further. Just pick a random code according to the degree distribution, it will perform well. So in doing so, I've sort of reduced the search space. Originally, I had to optimize over the class of LDPC codes for block length n. Now, all I have to do is optimize over degree distribution. Okay, that's loosely speaking the kind of intuition that you should take. Any questions? So this is sort of the first high level simplifications or assumptions that we'll make. We'll make further simplifications. So right now we have gone down from specific LDPC codes to an ensemble of LDPC. But even analyzing the ensemble is not too easy. But the nice thing is that the belief propagation algorithm is a local algorithm. It just takes messages from its neighbors, then sends it to all the other neighbors. Okay? So what we will do is we will analyze the so-called, so to study this particular quantity, the average error probability we look at the so-called the computation graph. Correct. Correct. It also depends on n, but nothing more than that. So for this we look at, well, of course there's another thing which it depends on, and that is p, the probability of erasure, because it depends on the channel. But anyway, that's implicit. So let's pick an LDPC code. So let's fix one particular example. Let's say that I have this particular LDPC code over here. Now for this LDPC code, again, this is a local sort of algorithm, right? So suppose I want to find out what is the probability that, say, the second bit is in error. So this is 1, 2, 3, x. So let's say that I run the belief propagation algorithm for, let's say, L iterations. Maybe I just run it for one iteration. And then, and I want to find out, say, what is the probability that the second bit is in error, second code word bit is still in error, or in other words, it is the, what is the probability that it has not been decoded? Then which are the variables which actually influence whether or not this is decoded correctly? Right? So for this, we look at the computation graph. You start with x2, right, and progressively kind of unravel this particular graph. You look at its neighbors, and then neighbors of neighbors, and so on, up to L iterations. So you basically want to find out which all nodes essentially influence the decoding of x. Right? So in this case, let me label these as C1, C2, and C3. So if we just run it for one iteration, we just run the algorithm for one iteration, then what happens? So x2 would get messages from C2 and C3. We're sort of going backwards in time now. Okay? So in the end, you will decode x2. But in order to decode x2, you will do it using the messages from C2 and C3. Right? So C2 messages from C2 and C3 will be used to decode x2. But what do messages of C2 and C3 actually depend on? So C2 depends on just x2 and x5, but again x2 is but then the message from C2 to x2 depends on the other neighbors, right? So it depends only on x5. This is x5. And what about C3? C3, now the message from C3 to x2 depends on the messages sent from x4 and x6. So x4 and x6. All right, so this is useful. So this is sort of, so therefore, if I just run the belief propagation algorithm for one iteration, then the decoding of x2 will of course depend on x2 itself or y2, but also it will depend on x5, x4 and x6, or y5, y4 and y6. But then it doesn't depend on the values of say y1 or y3 or y1 or y3, right? Because you're only using this sort of local information. But then now if I, let's say, run it for 2 iterations, then what does this computation graph look like? Now x5, where does x5 get its messages from? x5 gets its messages from C2. So I'll draw another copy of this, right? But in fact, I should not be drawing a copy because the information that it gets from C2 is basically useless information, right? Because what it is getting is from x2 itself. So basically in the computation graph, you don't repeat vertices. Okay, so now x4. Let's look at x4. What does x4, where does x4 get its messages from? It gets it from C1 and C3. But I already have C3 here, so I don't want to repeat. Okay. Okay, so now what about x6? x6 is again connected only to C3. So that's just about. Now what is C1 connected to? Right, so C1 to x4. So this depends on messages from x3 and x1. One x3. So this is assuming that, so this is, it is L equal to 1, and this is if L equal to 2, if you run it for 2 iterations. Okay, so now let's just focus on L equal to 1 iteration. Okay, just run it for 1 iteration. Now what is the probability that x2 is not decoded correctly? Or in other words, at the end of 1 iteration, what is the probability that x2 is still an erasure? So for that, x2 would of course have to be an erasure. So y2 would have to be erasure. Copy. So what is the probability that at the end of 1 iteration, x hat is in erasure? So this is in erasure if y2 is not an erasure, then x2 hat will not be an erasure. That's clear. Okay, so x2 is the actual code word bits. Right? Y2 is the received sequence. So yn is the received sequence. So xn is a 0, 1 sequence, but or variables which correspond to the code word, whereas yn is the actual received sequence. Right? So if y2 is not an erasure, basically it's a 0, then there's nothing, then all of this information is basically redundant. You don't have to do any more decode. So it remains an erasure if y2 is an erasure and if the incoming messages, if both incoming messages are erasures. If either one of them is not an erasure, then you can select x2 hat equal to 0 or 1. That comes from the belief propagation algorithm. So this times the probability that the message from E2 to X2 is an erasure and the message from T3 to X2 is also an erasure. Right? Okay, so that is fine. What is the probability that this happens? It is P, the probability of erasure for the BEC, times what is the probability that this message is an erasure. So this is an erasure if this message is also an erasure. Remember what happens at each of the check nodes. You take all the incoming nodes, all the incoming messages. If any one of them is an erasure, then the outgoing message is also an erasure. If all of them are zeros or ones, then you take the XOR of all of them and send it to on the outgoing edge. So the outgoing message is an erasure if any one of the incoming messages is also an erasure. Okay. So this is the probability that the message, so the probability that this is an erasure is equal to the probability that the message from X5 to C2 is an erasure times the probability that the message from X4 3 is an erasure and or the message from X6 is an erasure. Right? Okay. Now again, we're making some assumptions over here when we're trying to analyze this probability of error. In this, I sort of went from this particular graph to this particular tree. And in general, this need not have this nice tree structure. In particular, there could be sort of cross connections and so on. But nevertheless, I'm writing these probabilities as product of probabilities, which means that I'm assuming that these are independent. Right? Now, if all of these, if this computation graph is truly a tree, then all of this is fine. Because there's no dependence. All of them depend on independent yi's. They're all distinct yi's, and therefore, since it's a discrete memoryless channel, they're all going to be independent. But otherwise, you can't make this assumption. But nevertheless, I'll still continue with this calculation just to see how things can, how the analysis works and why we can make these simplifications. Okay, so this is P times, so this message is an erasure if Wi-Fi is an erasure. And what is the probability of that happening? It is P times the probability that this message is an erasure or this message is an, and that happens only if Y4 is an erasure or Y6 is an erasure. What is the probability of that happening? It is basically 1 minus the probability that both are unerased. And what is the probability of that? What is the probability of erasure is P. Okay? What is the probability of it not being erased? So it's 1 minus P the whole square. So this is the probability that both of them are unerased, and this is the probability that only at least one of them is erased. So this is P square into 1 minus P the whole square. So for a given graph, right, we can find the sort of, potentially this is a way to calculate the probability of error or the probability of bit error after L iterations. This is just for L equal to 1, and the 2 for this very specific LDPC. But as you can see, this is not a clean way to do it. You can't take a graph and then find out the neighbors, and then that's extremely difficult to do. And as soon as you just go to L equal to say 4 or 5 iterations, it becomes computationally very expensive, right? But now what we're doing is we're choosing a random LDPC. And in a random LDPC code, for random LDPC codes, let's say drawn according to a particular distribution, as you let n to grow very, very large, nice things begin to happen. So firstly, the computation graph for any of these xi's is going to be a tree. And this happens with very, very high probability. Okay, which is a nice feature, which means that all of these messages are going to be kind of independent. But then this is under a condition for any finite or fixed L. So you fix the number of iterations, okay, let's say 100 iterations, and you take n to be very, very large, much larger than 100. Then the probability that this happens is close to 1. So that's in a sense, this is taken care of by that assumption that the graph is locally tree-like, which means that it doesn't have any short cycle. That's sort of the assumption that. So that's one particular assumption that we will make. So therefore, instead of looking at this computation graph, it suffices to look at another class of graphs. So remember from the LDPC code. So our goal is to analyze the LDPC code. So have LDPC code which we want to analyze. Now since we fixed L, analyzing the performance of this LDPC code or a random LDPC code from over the BEC essentially involves analyzing the computation graph. The computation graph. And then if n is very, very large, then instead of looking at the computation graph of a specific LDPC code, all you need to look at is the so-called computation tree. And in fact, we look at random computation. So we study, so we started on, so this is a class of graphs, random graphs that we want to study, or a class of random codes that we want to study. But instead, we'll see the performance of the belief propagation algorithm over this class of random trees. And then basically one can show that the probability of error, or probability of bit error for this computation tree turns out to be almost the same as the probability of error of decoding VP over this random LDPC. That's sort of the connection. So in terms of analysis, we'll analyze the computation tree, but in fact, we'll be making predictions for the LDPC code itself. So what is this class of computation trees? What I call the tree ensemble. The tree ensemble. You see two ensembles, or two classes of trees. These are again random graphs, and these are specified for L iterations. Right? You run the BP algorithm for L iterations. So in some sense, it's going to be a tree of depth 2L. Again, if you view them as check nodes and variable nodes forming one particular level, then it has L levels. And we'll see two different classes. One is what I call from an edge perspective, and that will be denoted by this arrow. This is for a particular degree distribution, or it will be from the vertex perspective, which will be denoted with the circle. The node, the vertex. So this is basically, it's a random construction, and the construction works as follows. So let me first specify how this is constructed. So step one, so initially it's an iterative construction. So it's an iterative construction, and let's see how to construct this from the edge perspective. Okay. So remember that if you think about it carefully, both lambda and rho, these are polynomials, right? And the coefficient is the fraction of edges which are incident on nodes of degree I. So if you sum up all the coefficients, what do you get? Correct. But what will it be equal to? Yeah, correct. But if you look at lambda, so if you get lambda of 1, but what is lambda of 1 going to be equal to? Remember, you're summing up, let's say, fraction of edges incident on nodes of degree, say 2, plus fraction of nodes incident on nodes of degree 3, and so on. So you're summing up fractions. You add them up, what would you get? Correct. But it'll always be equal to the same quantity. That's capital lambda of n. So capital lambda of 1 is equal to, but then if you look at lambda of 1, lambda of x, again, go back the definition of lambda. Remember, so this is lambda of x, right? So what would be the sum of the coefficients? It would be just lambda, this evaluated at x equal to 1. So what is it equal to? Always equal to 1, right? And if you think about it, that's natural, right? You're summing up the fraction of edges which are incident on nodes of degree I, and obviously they should all sum to 1. So in other words, both lambda and rho, if you just look at the coefficients, they form probability mass function. So all the lambda, all the little lambda i's are all greater than or equal to 0, and they sum to 1. So that's what we'll make use of here. So let's see how to construct TL of lambda and rho. So first, for L equal to 0, T0 of lambda comma rho, this just consists of one vertex. Nothing else, no edges. Right? This is basically going to be a variable node. Okay. So now suppose that we have constructed, so for general L, we know how to construct, let's say, TL minus 1 of lambda comma rho. What do? You first pick a random tree from according to TL minus 1 of lambda comma rho. Okay. And replace each leaf or let me put it another way, for each leaf, which are all going to be variable nodes, connect let's say I check nodes or I new check nodes with probability lambda I plus 1. Okay. And for each of the newly introduced check node, connect j new variable nodes with probability rho I plus 1. Okay. So let's maybe see this using an example. Right? Let's perhaps take, we need a valid degree distribution. So let's take the following example. So let's say lambda of x is x and rho of x equal to square by 4 plus cube by 5 5 plus 4x to the 4 by 5. So how does this construction work? Let's suppose I want L equal to 1. I want to find P L P1 for this particular lambda and rho. Okay. So first T0 just consists of one vertex, one variable. Now for this, I'm going to associate a random number of check nodes. So think of it as the number of neighbors of this particular variable. Right? Now what am I going to do? It can have either 3 neighbors or 4 neighbors. Well, actually this is from the edge perspective. So actually the variable node can have either 4 neighbors or 5 neighbors. Right? Because this is summation overall I lambda I x raised to I minus 1. Right? But even then, I'm going to choose 3 neighbors with probability 1 by 5 or 4 neighbors with probability 4 by 5. So maybe I draw basically I toss a coin with probability 4 by 5. I pick 4 neighbors, or with probability 1 by 5, I choose 3. Either 3 or 4. I pick these with these probabilities. Suppose I chose 4. So basically I have okay. Now for these, I'm sorry. I think here this is x power I minus 1. Right? So basically, I'm going to pick either 2 neighbors or 3 neighbors because it's I minus 1. I minus 1 equal to 3. So I should be picking I neighbors with probability lambda I plus 1. So I'm picking 3 neighbors with probability 1 by 5, with probability 4 by 5, and 2 neighbors with probability 3, 1 by 5. Suppose I pick 3 neighbors with probability 4 by 5. So this probability is with probability 4 by 5, I pick 3 neighbors. Okay, so for each check node, I'll pick a certain number of neighbors. So how many neighbors do I pick? Either it is 1 neighbor, right, or 2. I got this a little. Let's redo this. So this is rho. This is lambda, and this is I minus. So now Therefore, the variable nodes can have degree either 2 or 3. Right? Variable nodes can have degree either 2 or 3. So I'm going to start with T0, which consists of a single variable node. And now I'm going to choose a certain number of neighbors. I'm going to choose either one neighbor with probability half or two neighbors with probability half. Suppose, so with probability half, I pick the number 2. So for this variable node, I associate two check nodes with probability. Now for each check node, I choose a number, either 3 or 4. The number 3 is chosen with probability 1 by 5. The number 4 is chosen with probability 4 by 5. So for this check node, I choose one of these two numbers. Maybe I choose 3. So then I associate 3 neighbors. This with probability 1 by 5. Or I choose 4 neighbors. This happens with probability 4 by 5. So the probability of picking this particular graph is half times 1 by 5 times 4. Right? So that is whatever 4 divided by 25 times 2 or 2 by 25. So with probability 2 by 25, I will end up with this particular graph. This is for L equal to 1. Now again, there are multiple possibilities. So either I could have chosen this particular graph, or I could have chosen just one number. Right? I could have chosen one neighbor with probability half, and then I could have chosen whatever, either 3 or 4 descendants with probability either 1 by 5 or 4 by 5. So probability of ending up with this particular graph is half times 4 by 5 is 2 by 5. And so on. So this is for L equal to 1. You can again construct for L equal to 2. So basically you pick one of these. So again, you start from the root, you keep adding its children one after the other according to this random rule. So basically you're generating a random number of children for each node according to this particular problem. Okay, so that is the graph. That is the ensemble of trees TL of lambda rho from the edge perspective. We need another ensemble of trees, which is basically from a node perspective. Yes. Doesn't matter. It's a random construct. Okay? So with probability 2 by 5, you will end up with this. With probability 2 by 25, you will end up with this particular. But all of them are probable to occur. Okay. From the node perspective, there's only a very minor modification to this particular construction. And that is in construction of the first level. Right? From the node perspective of lambda rho, same as rho, but for children of T0 on from with probability n. So remember, we had a lambda of x and a rho of x. Right? Now, lambda of x, so basically we choose h are drawn in Li. So in the previous case, remember, what we had to ensure was that in this particular construction, right, you look at any neighbor, if you look at the degree of any of the intermediate nodes, not the root, not the leaves. You look at the intermediate node, what is the degree of this? It's either 4 or it is 5. Correct? This is exactly what you would see in the check node. In the check node, degrees can either be 4 or 5. Right? Similarly, if you sort of drew this even more, so if you look at these intermediate nodes, these have degree either 2 or 3, right? Which is the actual degree distribution of the variable nodes, either 2 or 3. But then the root itself has degree 1 or 2, right? Which is 1 less than the actual degree distribution. Degree distribution, actually the degree should be either 1 or should be either 2 or 3. And of course the leaves have degree 1 always. There's nothing with that. So the main difference between the drawn from the vertex perspective and from the edge perspective is basically what is the degree of the root, right? In this case it is either 2 or 1, right? But then if you try to construct it using the vertex perspective, then it would either be 2 or 3 instead of it being 1 or 2. Right? And what is the probability with which you draw the neighbors? It is not drawn according to lambda of x, but it is drawn according to L of x. Okay? So it's only for that first level, only for the children of the root. For everything else, it is the same as before. Okay? So in other words, if I had to sort of randomly construct, then I have this, right? I have lambda of x. Let's just do this. To take this particular example, what is L of x equal to? No, it's obtained by integrating this. Yeah. Okay. You will still have to normalize this. Divided by 1 by 4 plus 1, which is going to be in x. Okay. So now if I want to construct T1, the node perspective of lambda rho, then what do? I start with the root. I pick either 2 or 3 with, I pick 2 with probability 3 by 5. I pick 3 with probability 2 by 5. Okay? Maybe I pick 2. So the probability of this happening is 3 by 5. Now from here onwards, I'm again picking according to lambda or rho. So I draw either 3 or 4 with probability 1 by 5 or 4 by 5. Maybe with probability 1 by 5, I pick 3 children. Probability 4 by 5, I pick 4 children. Right. Or this could have been a different realization. I pick 3 neighbors with probability 2 by 5. 3 children with probability 2 by 5. And from here onwards, I pick either 3 or 4 neighbors. So this is how the random construction works. So again, what is the utility of actually studying this? Now, the nice thing about this is that now we've sort of lost all the labels of the on the nodes, right? This is some arbitrary variable node. These are arbitrary check nodes. So going from the LDPC code, we went to the computation graph, which is specific to that particular factor graph or that specific code. But now we are trying to sort of remove all the label information, and we're constructing this particular tree. Right? This is a random tree which is constructed now, which is purely according to this. What we will now do is characterize the average performance of the belief propagation algorithm run on this particular tree. Right? Suppose that each of these had, now you think of this as a code, right? And for each variable node, we associate all the zeros, and each zero is erased with probability p, and it's left unerased with probability 1 minus. And now for this, we want to know what is the probability of error. It turns out that the probability of error, so if you look at the large block length limit, you let n tend to infinity, then the performance of the LDPC code basically converges to the performance of the belief propagation algorithm run on this particular tree. Right, so that's sort of main result over here. It says that the limit n tends to infinity of the average performance of the LDPC code bit error probability if you run the belief propagation algorithm for row with probability bit error equal to p. This basically converges to the probability bit error of the belief propagation algorithm, which is run on the following tree from the node perspective, L of depth L, where lambda Yes, right now we reduce the problem from studying the ensemble of LDPC codes to the problem of studying this ensemble of trees. And now what happens for the ensemble of trees? We still have to analyze the probability of error for this, right? So for this, it turns out that the probability of error can be obtained by a very simple recursion. So basically, you fix any degree distribution, lambda and rho, okay, and define x minus 1 to be equal to 1, and let xl to be equal to p times lambda of 1 minus rho of 1 minus L minus 1 or L equal to 0, 1. Okay, so there is this recursive definition, which is purely a function of lambda and rho, right? Then for any L greater than or equal to 0, the probability bit error of rho over the BEC with probability P. This is exactly equal to P times L of 1 minus rho of L minus. Okay. Now again, this seems hard to parse. So let's just see what would happen if we chose a regular LDPC. Okay. So for a regular LDPC code, lambda of x is simply so if we chose so for maybe a DVDC regular LDPC code, have lambda of x is equal to x raised to dv minus 1 and rho of x equal to x raised to dc minus 1. Right? So what do these recursions look like? So xl is equal to p into this is basically dv minus 1 minus xl 1 whole raised to dc1. So basically what you can do is you start with x minus 1, compute x0. So x0 is equal to p into 1 minus of 1 minus 1, x minus 1 is 1, dc minus 1 whole raised to dv minus 1. But then this quantity is 0. So therefore this quantity is 1. 1 raised to dv minus 1 is just p. x1 is then p into 1 minus x l minus 1 p whole raised to dc 1 whole raised to dv minus. And similarly, you can look at x2, which is p into 1 minus x1 whole raised to dv minus 1 whole raised to dc minus. Now, if you want to compute the final performance for L iterations, then XL is basically going to be equal to P into 1 minus XL minus 1 whole raised to P minus 1 whole raised to dV, right? Because at the last step, you take L, not lambda. For this case, this is lambda of x, but L of x is x raised to dv. That's sort of the difference between this quantity. Any question? Correct. So the edge perspective essentially gives you the probability. Essentially, what you're tracking here is the probability of a particular edge or a node being in erasure. So from the edge perspective, what you basically track is what is the probability that for a given vertex, the outgoing message is an erasure. Okay? But from a node perspective, what you track is what is the probability that after L iterations, the final decoded symbol is an erasure. Or from an edge perspective, after L iterations, what is the probability that the outgoing message is an erasure? So those are that is the only difference between these two. All right. So in the next class, we'll see some sort of simulations and see how we can sort of evaluate this, and then so this gives us a way of evaluating a degree distribution. Just a simple equation that it's easy to implement and compute. But then now we want to let's say that we want to optimize our degree distribution. How would we do that? How is it possible to do that? So we'll both evaluate performance and see how to optimize, and then later on we'll see how to generalize this to channels other than just the BEC. Let's stop here.